Okay, so we're kind of at the last of the series of lectures on modeling issues, and just to remind you, at the outset, we kind of laid out these four different topics. I don't know if you remember this lecture, but we did go over this slide. And so we've done the first three. We remember the first lecture, we talked about different types of models, linear, nonlinear, and that has an impact on how you fit those models, and that, which was the subject of the second lecture. How do you actually mechanically find the best fitting weights and what that means to minimize squared error and all sorts of things like that. And then we looked at this issue of cross-validation, because if you just fit a set of data, you may be overfitting, and we want an unbiased estimate of the true accuracy of that model. So we introduced the idea of cross-validation for that. And finally, we're at this last bit, which we'll get into, which is model reliability. And that's the focus of today's lecture. So the setup is like this. So again, we have some data, and we're talking about regression models. So we're going to try to predict some variable in that data set using some other variables. So you can call them regressors and input variables or whatever. And now that we've fitted a model to some data, in doing so, we've estimated some of the free parameters in that model. So think of in a linear regression model, that's just the set of weights applied to the regressors. And so one issue that we might be interested in is how reliable those weights are. In other words, how stable are those weights? Or another way to say it is, can we put error bars on the particular weights that we have estimated? And the reason this even comes about is something we've went really early on in the course, which is sampling error. So remember just talking about the mean. You have a population, you want to estimate the mean, you draw some samples, and given a particular sample, you get a mean, but you know that there's some uncertainty on that because of sampling. You could draw a new sample, and the mean will be slightly different. And you could do that many times, and then you can start constructing the distribution of the sampling error. And so that exact same problem arises when you're dealing with models. It's just that the modeling procedure is a little more complicated. The mean is easy. You just add and divide by the number of data points, but when you fit a model, that's slightly more complicated, but it's the same overarching issue, that your model may have some instability to it just because of sampling error. So let's look at some simple examples of that. And I guess one other aspect that we've already seen, and which we'll also use here, is we're going to use a particular strategy for estimating that variability, and that is bootstrapping. Remember, we bootstrapped in the case of univariate distribution. You can bootstrap to get an uncertainty on the mean or uncertainty on the median or whatever you were interested in. And that exact same strategy we can apply here. And so we're going to obtain an estimate of the sampling error, or error bars, on model parameters using that bootstrapping strategy. Okay, so this first example, our usual predict one variable in terms of another variable. We're trying to model y in terms of its relationship to x. And I'm going to tell you that, well, the true model that I generated these data from has a very simple structure. It's a linear model. And I guess I'm not plotting you what that model looks like, but as you can probably imagine, it's a straight line that goes kind of where my cursor is. And so given that sort of true underlying model, I've drawn 10 samples, not that many samples. I've drawn 10 samples from that underlying model. Of course, there's some noise, there's some variability around this line that I've kind of imposed in my little toy example. And so here are the 10 samples. They're highly correlated, you can just see by eye, and in terms of modeling, let's fit an explicit model to these data. Very simple model, linear model, y equals ax plus b. There's two parameters, a and b. So we could fit that model, and we could visualize a model going through these data points, and that model won't be exactly the same as the sort of true model that we're interested in, because we only have 10 samples. But it'll probably be close. So if we were to use the strategy of bootstrapping, how would that proceed? It's pretty straightforward, and it's very similar to what we saw with bootstrapping the mean. You basically take these 10 data points, draw a width replacement from those 10 data points, and each time you draw, you get a bootstrap sample. So you draw 10 points, because there's 10 data points here, with replacement from these data points we have, do something, in this case, fit a line, fit a model, and then we're going to repeat that process for every single bootstrap we draw. And so I've done that here, and I've plotted I've plotted one thin gray line for each bootstrap that I've performed. And so this gives you an immediate intuition for some uncertainty on this model that we're learning from the data, right? Depending on the bootstrap, the line can be slightly more steep or slightly less steep, and so forth. I guess I didn't plot if you didn't bootstrap and just fit the data directly, I didn't plot that line, but you might imagine it's basically going to go somewhere in the middle of all these gray lines. So by bootstrapping, we get some intuition of what this uncertainty is. And now let's sort of look at the one thing that we kind of wanted to know about, the A and B parameter. Maybe you're actually interested in what the value of A and or B is. And so in this part of the figure, I'm just going to do a histogram across all our bootstraps. So in this left panel, we're just looking at the A parameter, and we bootstrapped, I don't know, 500 times maybe. I don't know how many simulations I did. And if I just do a histogram across all of those simulations of my estimate of A, it looks something like this. And I've put a red line here, just summarizing the central, I think 68% of this distribution, which is kind of like a standard error. So if you remember, plus or minus 1 standard deviation encompasses 68% of the normal distribution, and these distributions aren't really normal, but so that's why I can use a sort of percentile-based strategy to get at something similar. So this is something like an error bar on the A parameter here. And so we can do the exact same thing for the other parameter. The other parameter also is part of the model, B, and we plot a histogram of those estimates and also a 68% confidence interval on B. So you can kind of compare this error bar on A, and I told you up front that the true model has A equals 0.5 and B equals 2, and it's close, but the error bar is big, so you can kind of see that. In this, we're a little bit closer to B than we are for A to the true answer, but all right. Question?
Could you explain, what does it mean to have a distribution of parameter estimates? Like, I guess I thought that A and B were fixed numbers.
Yeah, so, well, it depends on what our semantics here. So I told you up front that these are all simulated data coming from a fixed model. So every time I generate a sample from this, I basically look up what is the right Y value, and then I add Gaussian noise to generate some samples. In this case, I use the phrase distribution of parameter estimates, and all that means is we're plotting a histogram of all the different parameter estimates we get from our different bootstraps. And the issue is we don't know what A is, right? I told you what it was, but you can just sort of ignore the fact that I told you that, and all we know is we want to fit this model, and A is unknown. And we can learn A from a given set of data, these 10 data points, and that's one number. You can get your best estimate of what A is, but we know that there's also sampling error, and so that's what gives rise to the fact that it's actually a distribution, or there's some uncertainty in what A is. Does that answer your question? Okay. So this is a simple example, and
why wouldn't you just use all of your data to calculate?
Oh, you can. Oh, certainly you can just say, I want the best estimate of A, and so I'm just going to fit my 10 data points. But then you don't have a sense of the uncertainty. And that's the point of doing this bootstrap procedure. Now you can see that there's actually quite a bit of uncertainty on A.
So I guess, would this be applicable, if you had, say, different experiments, on different days, and you got, those data for one day, and you have, that same sort of, structure of data the next day, and then you calculate, a model each day, sort of?
Yeah, so by estimating the uncertainty on A for these 10 data points, that'll hopefully be predictive in some sense of the variability you will get if you actually had done the experiment again. I mean, that's kind of that's sampling error. If we were to draw 10 new data points, suppose repeating this experiment on the next day, or getting 10 new subjects, or however you want to think about it, and you fit the model again to that new fresh data, it's not going to be exactly, the A parameter is not going to be exactly the same, and that's exactly the uncertainty that we're trying to get a sense of.
But does that assume that your sample is unbiased? Like you could say like if you're sampling a class for like 2 days, right? And then this sample that you're drawing is from like say all the top students in your class.
Yeah, all of this assumes that whatever you've done to sample your data, it's hopefully a good sampling strategy.
Okay.
Like, I mean, especially this bootstrap idea, you're using this particular sample quite heavily as representative of some underlying population. And but I mean, this is an issue that's sort of beyond the scope of what you can do with the data. If you know that these 10 points are not representative of anything, then doing the bootstrap's not going to help you, right?
Is there a general heuristic for like how many sample points you want, or does that depend case by case depending on like the type of
More is better. I mean, it kind of depends on what you're getting at. If you want to know, like, if you can put a bound, like I suppose you need the confidence interval to be sufficiently small, so you can say, how many subjects do I need to achieve a certain confidence interval size, and then you can run simulations, kind of like this, to see how many subjects you'll need to achieve that. So that's certainly one thing you could do if that's what you cared about. But it's hard to say in general. In general, you need X number of subjects. You always need to specify in order the goal. Like, I need this many subjects so that something. And that something kind of depends on your situation. All right, so I guess it's useful, given these questions, to kind of look at a slightly different case. So this example is exactly the same. I just increased the sample size. So the same sort of underlying function, and we're happy to fit the same model, linear model, trying to predict y from x. And the only thing that's changed is now we have 200 subjects instead of 10. And so if you do the whole bootstrapping strategy, so now we have given our pool of 200 subjects, we draw a bootstrap sample, drawing with replacement from these points a sample of size 200, and you fit a line. Then you draw another one, and you fit a line, and so on and so forth. And these are all the lines that result when you do that. Just compare from top to bottom, you can see, hopefully, that these lines are tighter. They tend to be more stable from sample to sample. And that directly corresponds to the idea that our stability of our estimates of the parameters of the model A and B should be much better, much more stable from sample to sample. So we can look at this side, do a histogram of our A parameters across all those bootstraps, histogram of B, plot a little confidence interval using a percentile method. And as you can see, these red lines are much smaller than these red lines, which is just another way to say that we have much more confidence, or the reliability of our estimates is much better, or the stability of our estimate is much better in this case because we have many more data points. Any questions on this figure?
So
Oh,
if you have
okay.
too many data points, could you run into an overfitting issue, or is that dependent?
Well, remember overfitting is kind of a completely different issue. That was the previous lecture. So, and actually, now that you asked about it, it's actually the opposite. I mean, the more data you have, the less, generally speaking, the less overfit you will be. So more data is always better. It helps your stability of these parameters that you might be interested in. It also allows you to be less overfit, or another way to say it is allows you to fit more complicated models, to learn more subtle effects in your data if you have more data points. So you always want more data until your computer explodes. All right, so there are a couple other smaller issues that you can read about in the lecture notes. I don't think I'll even mention that at this point. But one issue that I made a little slide about is this issue of correlated errors. And the reason this even comes up is that when you're dealing with models, you probably have more than one parameter that you're interested in. So you can contrast the case with like, oh, we're estimating the mean of the population. That's just one thing. So you don't even have this issue of correlations and so forth. But if you have even like a linear model, as we just saw, there's two parameters. So that immediately means there may be some interaction in some sense between those parameters. And so this concerns the case of a simple case of, suppose you have a linear model and you have two regressors. And let's use an intuitive example of, suppose you're using height and weight to predict, I don't know, height and weight to predict. Say what? Basketball ability. Good, great, awesome. That's a concrete example. So that's, or suppose we're going to use linear regression to do that. So you measure some subjects, you measure their heights, measure their weights, and you also measure their basketball ability somehow. Number of free throws, or actually you can do free throws just what, you don't need height and weight. Anyway, whatever you measure, and you're doing, and let's say we're using linear regression to optimally predict basketball ability based on height and weight. And height and weight, of course, are correlated. That makes sense, and we could find this out empirically if we wanted to. And so these are some issues that arise once you have correlated regressors. So let me start with this case. So our two regressors are x1 and x2, and we have some weights that we're trying to estimate on x1 and x2 to predict y. And we're first going to look at the case of no correlations between the two regressors. And so now we're going to plot, for sake of exposition here, an error surface. So remember, when you're fitting a model, you're trying to twiddle the weights to minimize error. And in this case, when x1 and x2 are uncorrelated, the error surface will have a very specific shape. It'll be kind of spherical or symmetric, and it looks kind of like this. So imagine an upside down bowl, I guess, that is isotropic, or, you know, it's not extended in any direction. It's kind of symmetric, radially symmetric. There you go. And we're not looking at it in 3D. We're kind of just using color to represent the fact that it's isotropic. And so this is what you might, if you were to actually have data and calculate out and visualize the error surface, it might look something like this. And so let's just go through the axes. So remember, we're trying to determine the optimal weights. So W1 can range like from any number of values, and W2 can also range from different values. And if we were trying to fit this model to some data, we would want to find the minimum of this error surface right there. But for the sake of this slide, we're actually interested in not just finding the solution. We actually care about the structure of the error surface around that solution, because that's going to tell us something about what the heck this slide is about, namely something about the stability or variability of these parameter estimates we get, right? So when we fit one model, we have a fixed set of data, we fit a model, we get that one point. But now in this lecture, we're talking about how stable is that point? Like, how confident are we that the proper slope on, say, height is 0.4 and the proper slope on weight, being the other regressor, is 0.4. So you can kind of think of this, the error surface is specific to the specific sample that you have. So suppose you sample 200 subjects. You get one error surface out of doing that. But think about what the error surface means. So all of these points in this space, so if W1 gets a little bigger, a little bit smaller, or W2 gets a little bigger or smaller, notice all of those sort of cells are dark. And dark, I guess I'm not giving you a color bar, but dark means low error. And they're all low. This could be like a squared error of 20, and this could be a squared error of 21 and 22, and then maybe the optimum is 19. So they're all really, really close together. And so the intuition then is it should be relatively easy to kind of move around in that space because of sampling error. You got your sample of 200 people, but maybe if you added one more person to the sample, this error surface would kind of shift a little. And I mean, it definitely would shift. And the idea then is your optimal solution for that 201 size sample might be a little bit different than 0.4, 0.4. It might go up to 0.43 and then 0.39. And so the structure of this error surface is basically going to map onto the stability, or rather the instability of these weight estimates. And so on this side, what I've done, I think I've actually done real simulations given a specific model, and so each dot here is the result of one of my simulations. So I think probably I just drew a new sample and did this whole fitting procedure, and I did that many times just to kind of simulate what would happen with repeated sampling. And as you can see, they're all kind of clustered around the optimal solution, but they're scatter. So any given simulation, the specific configuration of weights you might get are slightly off. And so this is the sort of instability or uncertainty in the weights. And again, I plot little, if you just take the marginals of this is a two-dimensional distribution, right? Instead of a histogram, we can visualize this using a scatter plot, or you could actually plot a 2D histogram. And if we can just marginalize, sort of ignore W2 and just look at W1 and look at its distribution, and then plot a little bar indicating the 68%. Middle, central 68%. And you can also do that for the other parameter. So what we're looking at here is really analogous to what we just saw in the previous slide, except that we're looking at this in 2D. 2D because there's two parameters in this model. I guess in the previous slide there were also two parameters, but we kind of glossed over the fact that there may be interactions between these two parameters. So here we're actually explicitly looking at that. Okay, so this whole row was just the case of x1 and x2 are uncorrelated. And so what we want to do now is look at the case of when they're correlated. So now we actually have the case of something like height and weight. If height and weight are highly correlated, it's in some sense they kind of tell you the same thing in terms of predicted power, right? If you know someone's height is 6'5", you kind of already know their weight is 240 maybe. So they're kind of redundant almost. I mean, the more correlated they are, the kind of more redundant it is. And so let's just imagine x1 and x2 are highly, highly correlated. So in that case, again, we're talking about the case of put these variables in a linear model, and we have two weights that we're trying to estimate. And if you have a situation like this and actually look at the error surface for a set of data, it might look like this. So immediately it should be obvious that the kind of shape or structure of this surface is very different than what we saw previously. So this error surface, as usual, has some minimum, and that's indicated right here. So W1 is 0.2, W2 is 0.39 or 0.35 or something. But importantly, look at sort of what's black in the error surface. So here, the black was kind of isotropic. Any direction was kind of equally distant in terms of black, whereas here, the blackness is kind of elongated in a certain direction. And the idea then is that W1 and W2 are kind of trading off with one another. So let's be a little more specific there. So imagine that the weight, so the first weight, W1 on x1, if that weight increases a little bit, so if you go from, let's say we start from the optimal solution, 0.2, and if you just increase the weight on W1 by 0.2, so you go down over to 0.4, if the two regressors are very, very similar, then you can kind of counteract the increase in weight on x1 with a decrease in the weight on x2. So if you give a little more slope or a little more influence to height, you can kind of counteract the effect of that on the model by decreasing the influence of weight, because in some sense they're the same thing. They're so correlated. So that's why the error surface remains to be highly dark if I move diagonally. So I increased W1 a little bit, and if I just decrease W2 a little bit, I basically get a model fit that's almost identical And that just means the goodness of fit against the data will be almost identical. And that's exactly what we're visualizing here. So what that means then for our stability is that we get a very interesting interaction between the weight estimates. So essentially we're plotting, again, I did all these simulations. A dot represents one simulation of a specific optimal weight setting for W1 and W2, but intuitively it basically mirrors the structure of the error surface. So everything that's dark here is highly likely to kind of result in that kind of weight estimate. And the important thing is this cloud of points is elongated, unlike what we saw earlier. So this is saying we have a lot of uncertainty on W1 and W2 because W1 could be large, and you can kind of counteract that by a decrease in W2. So there's a large range of possible solutions in some sense because they kind of trade off with one another. And if you look at the marginals of each parameter separately, notice you have a lot of uncertainty on what the optimal value for W1 is, as well as W2. How do you know how much you want to offset the weights by? So given a fixed set of data, 200 subjects say, there is one optimal solution for sure. On the other hand, yes, you can say that's the optimal solution, but you should also keep in mind that there's a lot of uncertainty on that optimal solution, right? So does that answer your question? I'm not sure exactly what your question was, but I kind of thought that that's what you were getting at. I mean, given your data, the best you can say is the best guess, in some sense, is this point, and also report that, well, because of this high correlation between the two regressors I put in the model, there's also a very high uncertainty on that answer.
So, like, if you were going to report that, would you model, like, get the optimal fit on all of your data, but then also, like, calculate, like, this and report, like, the error bars?
Yeah, I mean, both. You kind of want to know both. You want to know, like, your best guess of what the answer is, as well as your uncertainty on that.
Because, how often is it the case that the optimal fit through all of the data is equal to the, like, bootstrapped optimal fit?
So I'm not exactly sure what you mean by the bootstrapped optimal.
So, like, if you had like 200 samples, and you find the optimal fit for that, and whatever parameter you want, you're calculating. But then, like, you bootstrap that, like, X number of times. Well,
So typically, your distribution of estimates across your bootstraps will more or less include your optimal fit, right? So if you look at our earlier examples, I guess I didn't tell you what the optimal fit, if you just fit the 10 data points, was, but it's presumably somewhere in the middle of this big distribution. So they're kind of the same. Okay. Empirically, they'll be very similar. So. Any other questions? So, so we motivated this in the context of a linear regression model, two correlated regressors, but this generalizes to, you have a nonlinear model. There may be weird interactions between parameters. So you could have ax to the n plus log x2 or something. And depending on the structure of your model, there may be interactions. I guess I'll just leave it at that. All right, so moving on. So we kind of are reaching the end of the conceptual stuff for this modeling stuff. So rewind your brain back to the last lecture. We talked a lot about overfitting, cross-validation, biased, and so forth. And so now we can kind of think about both concepts at the same time. So we called that, or at least I called that kind of stuff accuracy, quantifying how truly accurate your model is. And we're not talking about, only on your sample, because that's an optimistic estimate of your accuracy. We're talking about generalizing to novel data. So that was model accuracy, and then we just got done talking about reliability or stability or something, whatever term you want to use. And I guess it's useful to kind of contrast what's the difference between these two. Both of these are in some sense good. You want accuracy, probably. You want something that's reliable, probably. But they're not the same, and that's what this slide kind of is intended to explain here. So we have a little 2x2 setup: accurate, inaccurate, reliable, unreliable. Of course, these are just kind of depends on quantitatively what your threshold is for what is accurate. But anyway, so let's just start with this first case. So each red dot is a data point. See the legend down here, and the data were simulated as usual from some fixed model, so that's given by black. So given the black line, I assume there's some unexplainable noise around the black line, and that's what allows me to sample some points from that. And then finally we have this blue line. Hopefully you can tell there's a blue line, there's a solid blue line here, and there's also a sort of a shaded region around the blue line, which represents this. I obtained this using bootstrapping. So I took these data, these red dots, I fit some model, it doesn't matter what the form of the model is, and I bootstrapped that, and I looked at across all the bootstraps how, what's the spread of this line fit here is, and then I sort of summarize that using this shaded blue area. So I think I used, as usual, the 68th percentile of that model fit, just to give you some indication of the stability of, or the reliability of that model fit. Okay, so this scenario is what I'm labeling accurate and reliable. So reliable is the easy one. So it's reliable just because of the fact that that error bar on the model, so that blue shaded region, is very, very small. So it's with repeated samples, and that's what we approximated by doing this bootstrap, we know that the model fit we will obtain will be very, very close to what we are observing in the sample we have. So that's pretty straightforward. Does everyone see that? So this particular model that we've obtained has a very small error bar, meaning it's very reliable. And then it's accurate, and that can see that just because the dark blue line is very close to the black line. Of course, to establish, we of course don't have access to the true model in practice, so that's the whole cross-validation bit. But let's ignore the details of that for a second and just look intuitively why we can say the model we have, this blue line, is an accurate model. And it's simple. It's very close to this black line here, and it of course follows the structure of the data. You can kind of eyeball the data and see that. So this is the ideal case. Accurate is good, reliable is good, and everything's good, and we're happy. All right, so now let's look at this case. So exactly the same data points, just for fun, and therefore exactly the same sort of underlying model that I'm simulating, but the model has changed, and in this case you can kind of see that it's a linear model actually. But we've done the same thing. We've used a linear model. We've taken our data points in red, we've fit it, and we've bootstrapped just to get a sense of how reliable this fit is, and that's given by these shaded region here. So depending on your point of view, we would say, I think, that this model fit is quite reliable. It's a positively sloped line, and we can be pretty certain it's not going to shift around too much if we were to sample a new data set or anything like that, right? So the smallness of the shaded region kind of indicates that we're in the reliable row. So this fit's reliable, but the key point is it's not really that accurate for the data. So now for that, kind of eyeball the blue line against the data points, or the blue line against the black line. And the blue line doesn't really, it kind of follows the overall trend of the data, upward sloping data, and it kind of somewhere in the ballpark of the black line, but it's not great depending on your point of view. So this distinction that we've gone over so far is just already shows that these two aren't the same thing. You can have a very reliable model that you may not consider to be accurate. All right, so let's go on to another case. So in this scenario, we have, I guess I changed what the true underlying models. In this case, there's a simple linear relationship between x and y. So that's the black line. And I've simulated some data from that line. In this case, many fewer data points. So these data points were expensive or something, and so I only have like 20 samples. So that's in red. And given the data points, I've now fitted some model. Don't worry about what type of model, and I've bootstrapped that model to kind of look at its stability across sampling. And you can see here that the error bars are quite large on the model. They're so large that you can kind of imagine that you can draw a flat line, a horizontal line through the shaded region, which kind of means your uncertainty even includes the case of no predicted power, no correlation between x and y. So the error bars are large, and that is kind of the reason we would call this case an unreliable model. So that's bad. And it's also not very accurate, and you can see that. Does the blue match the black line very well? And this is all subjective, of course, but in this example I've said no. The blue is actually a wiggly thing that isn't very close to the black line. So this is the worst of all possible worlds, both inaccurate and unreliable. And then this last case is a kind of a weird case that you wouldn't actually find. In other words, how can a model be accurate but unreliable? Yeah, I guess I'll just leave it up. I mean, in theory, you might, if you have a very small sample, and you might, by chance, cross-validate really well, but in reality, that model might be unreliable. But that's probably just a thought exercise. I wouldn't worry about that case. Oh, all right. Yeah. Okay. So this is kind of a recap of both of these potentially complicated ideas, but they're actually quite simple procedures that we've gone through. So in the previous lecture, we looked at, again, accuracy and this cross-validation idea, and then just now we revisited the idea of bootstrapping. We actually looked at bootstrapping a long time ago. And these are both, just thinking about these both at the same time, these are very simple resampling procedures that you can do to data, and they're kind of independent of all the details of anything you do to those data once you resample. So you can apply these resampling procedures to any type of model. It can be linear, nonlinear, it can be really complicated, it can be really dumb and stupid and simple. And it's cool because it kind of equally applies to regardless of those details. So here's a little figure that just reminds you of all those issues. So in this case, we're going to use bootstrapping, the same bootstrapping procedure, to estimate the reliability of many different types of models. So I have 4 graphs here, exactly the same data points in each graph, again predicting one variable from another. And in this case, suppose we decided to use a linear model to kind of summarize and characterize the data. We can fit that model, we can bootstrap, in other words, resample the data, fit the model, and do that again and again to kind of derive the reliability of this linear model, and it would look something like this. Or if we had a different model, in this case a quadratic model, we can also bootstrap the data to kind of see the reliability of that kind of model. Of course, the fit's different, and we get a different quality of model, but we can also derive reliability using the same bootstrap procedure. And you can imagine how this goes on. There's these other types of models, remember, that you need to use some sort of nonlinear optimization technique to fit, but that's okay, right? That's a very different fitting technique, but the bootstrap doesn't care. The bootstrap is just the resampling part. So we can draw a bootstrap sample, use your nonlinear optimization to fit it, and then draw a new one, new bootstrap sample, and fit it, and so on and so forth. And we do that many times, and then we can also derive some sort of reliability measure on the resulting models. In this case, the shaded area is so small it's not even visible. So that's a very reliable model fit we're getting here. And then I have one last example, this crazy nearest neighbors model. It's kind of more of a procedure than a model, but again, the Bootstrap doesn't care. The Bootstrap says, you can bootstrap, you can fit your model, you can do this again and again, we can look at reliability of that. All right, so that's the Bootstrap, and then we can look at cross-validation. Here I don't really have a figure. I mean, the cross-validation, just think leave one out, so you might leave out a data point, fit the model to all the other ones, and then predict it, and do that for every single data point. Of course, that involves a bunch of computation, and at the end of the day, you might use a metric to summarize all of the predictive performance of your model. And so here I just have a little bar chart. So you can do that for a linear model. Again, the idea being it's independent of the specific model that you want to apply. So you can leave out a data point, fit any of these models, linear, quadratic, this exponential model, or this nearest neighbor model, to the training data, and then predict the left out point. And you can do that. And of course, that's just one data point. You might do that for all the data points in your data set, and then summarize the performance of each of the models using some number like r squared. And I believe these are actual values that I attained from these data. I actually did it. I need to just make a fake figure for you. And you can use this quantity, right? We're looking at accuracy in an unbiased manner. You can use that to kind of select what is the most accurate model, and it turns out to be this one, which kind of matches by eye what you kind of see in the data. But okay, so two different resampling techniques getting at two different aspects of model quality, and it can be generally applicable. It's not tied to any specific type of model.